16th of February, and I forgot to start vodcasting, so I'm sort of coming up with, I'm going to show you the screen that we've been talking about so far, and we're just going to continue with this discussion. But basically, what we've decided to talk about today, or what I've decided to talk about today, is the fact that we can use the ideal gas equation, PV is equal to nRUT, or PV equals MRT, for ideal gases. And the only correction that we are going to make in this class for the ideal gas law is for a compressibility factor, which, as you can see from this line of reasoning, is based directly on a correction to the ideal gas law, where this ratio would be 1 for an ideal gas, but whatever it turns out to be is its correction based on, it's loosely termed compressibility. It's not compressibility like a delta P term or a dP, d anything term. It's just a correction factor, really, for its deviation from ideal gas. All right, so the next question becomes, how do we find Z? And it turns out that Z is a function of something called reduced temperature and reduced pressure, which I'll describe for you in just a minute. Now, the idea, one of the reasons that we introduced this at this time is that this idea of reduced properties, or in other cases you'll hear, especially chemical engineers, petroleum engineers, we'll hear about pseudo-reduced properties, are ideas of where you are on that two-phase envelope with relation to the critical point. And these are properties that come up over and over again in calculations. So once again, if you have your two-phase envelope and you have the critical point at the top, the critical point is going to be some temperature and some pressure, and those temperatures and pressures are called critical temperature and critical pressure. So it turns out that the reduced pressure is the ratio of the temperature of the gas to its critical temperature, and similarly, the reduced pressure is the pressure of the gas divided by the critical pressure of that gas. So what this will do is give us a ratio, both of which are dimensionless, because we have temperature divided by temperature, so units go away. Same here, pressure divided by pressure, units go away. And we will have two values. We use those values of reduced pressure and reduced temperature in a chart to find the Z factor. Right? Now, this is in your property tables, and I'm going to find it for our tables. I'll show you what the chart looks like. I'll see if we have one back here. I'm not really sure where it is in your book, is what I'm telling you. And so I'm not going to make you watch me go through this. I wonder if we can find it. So if it's not in the tables in the back, it is in the it's in the body of your textbook. But let me go back up here and see. Yeah, I don't see it in the back. All right. So I was looking at, what I was looking at was the appendices and charts. And I don't see one that's going to give us the data that we need. So if we go into chapter 3 of your textbook, it is likely in the body of chapter 3. So let me see. And if it is, that means that my copy is really poor. All right. Hang on. Okay. My textbook says that this is in figure A15. A15 it says, but that's not right. That I don't have it right here. Oh, okay, there it is. Sure, A15. I just didn't read well enough. So let's go down to A15. Oh my goodness, and there it is. That is a nasty looking chart, but that's what we have to work with. All right.
Do they always look like that?
They always have this shape. They're generally more legible than this. So let me look. I'm going to look online and see if I can find a better one. What's that? I know. I looked at it. I was like, oh my goodness. So I don't know if that's going to work. Let's see.
Or is it more clear than buzz? Not necessarily.
Let's see if we can find a better one. Oh, that's cuter. That looks much better. All right. So this is from SDSU, South Dakota State University.edu. And basically they all follow the same shape. But what you will see is that on the vertical axis, you read compressibility factor. And on the horizontal axis, you read reduced pressure, which is that ratio, shows you right here, of pressure to critical pressure. And each one of the lines, this is referred to as a hurricane graph, each one of the lines corresponds to a different value of reduced temperature. Now the solid lines, which range from 0.6 up to 5, okay, represent reduced temperature, pardon me. The dotted lines refer to something called reduced volume or pseudo-reduced volume, and that is not a number, it's not a direct ratio, it's found by this formula. And generally speaking, reduced volume or pseudo-reduced volume will be a calculation, not just V over V sub R or V sub C. It'll be something different. So you have to refer to the key of the chart to determine what V sub R is. But some of the features that I'd like you to see about this, first of all, there's generally, when you have a generalized compressibility chart, there are two ranges for the bottom axis. The first one goes for a reduced pressure of 0 to 1. And then the other one will go from a reduced pressure of 0 to 7. So in other words, this is a greatly expanded. The data on this chart is, there's a lot more data. There's 7 times as much data. The entire other chart is comprised of from this point to this point. Okay? Now the other thing I'd like you to see is that they all converge at 1. In other words, a compressibility factor converges at 1, which means when you get to extremely low pressures, you get very close to ideal behavior. Makes sense, doesn't it? Same thing here, converges at 1. There was actually a misprint in one of the textbooks where everything converged at 0.9, and that was one of the things where I was like, wait a second, that can't be right. And so we wrote to the publisher, and he's like, yeah, okay, we saw that. But anyway, so they have to converge at 1. If you have a 0 here on your reduced pressure, has to converge at 1, or it's not, there's something wrong with the chart itself. All right, so we're going to use this in a few minutes. After we're going to do a problem with the ideal gas law, then we're going to do the same problem using finding the compressibility factor and correcting it. But we calculate the reduced pressure, and we find the, let's see, here it is. How do we find critical pressures and critical temperatures? Once again, we go into our tabular data, and what you'll see, generally in table A1, there we go. Over here, critical point properties. So we have the critical temperature in degrees Kelvin, the critical pressure in MPa, and as I said, this is pseudo-critical specific volume, which we don't use. We're not going to use that calculation. It's like sometimes you have to, but you always have to refer not to just like T over or V over V sub C. You have to do a different calculation, and that calculation is always illuminated right here in the answer key. Okay? So let's take a look at how to use this. So we use lots of tabular data. We make sure everything's in absolute units, and then finally we correct it using this, this curve. So let's take a look at a homework problem. Oh, and in your textbook, just FYI, section 3-8 refers to other equations of state, and we will not be using any of them. So this is it. All right, so the first thing that we're going to do is look at an ideal gas problem. And is that an elk?
Yeah.
All right, very good. Let's take a look at problem 3-70. 3-70 says a 2 kilogram mass of helium is maintained at 300 kPa and 27 degrees centigrade in a rigid container. How large is the container in meters cubed? All right, so for problem 370, we are going to use the ideal gas law. So that means that we have to assume ideal behavior in order to do this problem the first time. So what we are told is that we have a mass of 2 kilograms. Sorry? No, I think it's more fun this way. Sorry. There we go. Is that better? There we go. So we're talking about helium, and we have 2 kilograms of helium, and it's maintained at this pressure, which is 300 kPa, and at a temperature of 27 degrees centigrade in a rigid container. Okay, what does that mean? That means we can't expand it. That means the volume is fixed. Okay? How big is the container? What is the volume of the container? All right, PV equals MRT. V is equal to MRT over P. M is 2 kilograms. Let's skip R for a minute. T, we have to add 273 to get to degrees Kelvin. So that's 300 kelvins. Over a pressure of 300 kPa. So we need to go back into our tabular data and find a value of R that's going to make this work for helium. So I'm going to switch back over again. Helium, I have a gas constant of 2.0769 in kilojoules per kilogram Kelvin. The kilojoules and the kelvins look good. We're going to have to mess around with the kilojoules unless we're smart enough to look at the little asterisk right here. And it tells you at the bottom, the unit kilojoule per kilogram Kelvin is equivalent to a kPa cubic meter per kilogram Kelvin. So that's pretty handy, isn't it? That's a better unit. So that's telling us that we can use that value, and the units are, let's go ahead, kPa, meters cubed per kilogram degree Kelvin. And my number for helium is 2.0769. 2.0769. All right, let's do our units. Kilograms cancel out. Kilopascals cancel out. Kelvins cancel out. We're left with cubic meters. Is that a good unit for volume? It is. It's the best unit for volume. Well, because the problem asks for it. So performing that calculation, we have 2 kilograms multiplied by the value of our universal gas constant, or not universal, but our specific gas constant, 2.0769 times the temperature of 300 divided by the pressure of 300. Oh, that was easy. So it just should be 4 point something. 4.1538, or just 4.15 cubic meters. So the volume of our container is 4.15 cubic meters. All right, let's do something else. Let's find out what our compressibility is and what the volume would be for a real gas, even though it doesn't ask, but we need to do this, okay? So what we have here is we have our critical point properties, and we see that for helium, our critical temperature is 5 degrees Kelvin. That's very cold, isn't it? So we're going to have a huge critical temperature for this particular problem. It may not even be valid. Because well, let's go ahead and do it, just for the sake of calculation. For this problem, let's calculate T sub R, which is our temperature over T sub C. Our temperature is 300 kelvins. The critical temperature for helium is 5.3 kelvins. So our reduced temperature is 300 divided by 5.3, and that value is 56.6. I do not think we're going to get I don't think we're going to get a chart that's going to go up that high. But let's go ahead and finish our work. P sub R is equal to pressure over critical pressure. The pressure of this gas is 300 kPa, and the critical pressure for helium is 0.23 MPa, 0.23 MPa, and there is 1 MPa per 10 to the third kPa. So in other words, to get my units in kPa, this would be multiplied by 10 to the third, so it's 230 kPa. So that means that my reduced pressure then is just over 1. It's a value of 300 divided by 230. And so my reduced pressure is 1.3. All right. Now notice, these are dimensionless, right? I made sure that all my units canceled out. Reduced properties have to be dimensionless. All right. So if I attempt to go into the table at that temperature and pressure, what do I see about my values of T sub R? My largest value of T sub R is really at 5, and my T sub R is 56. So that's, yeah, that's a tough one, isn't it? So we're probably not going to find any value, once again, T sub R at 5. So we're clear up somewhere else, and that probably means that my compressibility factor is 1.1 or something like that. But we can't really pick it up off the table. All right, so let's get a problem that we can pick it up off the table. And let's do English units, just because it's so much more fun. Yay, English units. Let's do problem 386. E. Okay, 386E asks of us that we take ethane, which is a hydrocarbon, right? Just a little bit heavier than, heavier or lighter than natural gas, which is methane, in a rigid vessel, so the V is constant. And we wish to heat it from, let me read this again, heat it from 50 psi A and 100 degrees Fahrenheit until the temperature reaches 540 degrees Fahrenheit. The volume at 1, volume at 2 have to be the same, right? Because the volumes have to be the same because the container is rigid. What is the final pressure of the ethane as predicted by the compressibility chart? And we're going to find out. The first thing we have to do is to find out the volume 1 predicted by the compressibility chart. Keep that same volume and then go to 2. All right? Now, this is going to be a little bit more complicated because we don't have the pressure on the second case. So we would have to use a pseudo-reduced volume, which I'm not interested in having you do today. So the only thing I want to be able to do is to find what is the volume at time 1 based on compressibility. Okay? So we know that P times V over R times T is equal to Z, and we need to find the Z factor. To find the Z factor, we need to find our reduced pressure, which is the pressure of state 1 divided by the critical pressure of ethane. And similarly, the reduced temperature is the temperature that our ethane exists at divided by the critical temperature of ethane. So let's go back to the podium PC, and we're going to take a look at our tables. We need critical point properties, only this time instead of being in SI units, we're in English units. So we need to come all the way down to where we start getting into the English unit tables. All right, and I really don't like to use the word English unit, but I use that because it's 1E. You know, we're really talking about U.S. customary system units because they don't actually use these units in England, so just saying. But that's the deal. All right, so if we take a look at ethane, that has a formula of C2H6. And we have a reduced temperature, a critical temperature of 549.8 Rankine. And we have a pressure, critical pressure of 708 psia. So the first thing is we calculate our reduced pressure, 50 psia divided by 708 psia, which we'll do in just a minute. And we have to calculate our reduced pressure by taking our temperature, only our temperature's in Fahrenheit. And we have to add essentially 459 or 460 to get it in degrees Rankine. Like that. And then we can calculate our two values. Oh, you probably want to see that. There you go. All right, so doing the calculation then, first of all, I will calculate reduced pressure by taking 50 and dividing it by 708. And that gives me a value of 0.0706. Just call it 0.07. And then calculating our reduced temperature by taking 559, dividing it by 549.8, and we have a value of 1.01. So I'm just going to put that down, 1.01. All right, this is essentially 1. Now, we're going to use these values to find our Z factor from the table. And this is where, or from the hurricane chart, would be the better way to put it. So we come back over here and we take a look at our hurricane chart. The first thing that we notice is our reduced pressure is quite small, isn't it? It's 0.07, so it's right in between here and here. That means that we can use this expanded chart. That is the expanded chart. It's still just tiny. So our reduced pressure is 3 over from here, 1, 2, 3, right here. Okay? So the way that we do that is we carry that line straight up, which is quite difficult to do. And then we look at the solid lines of a reduced temperature of 1. And that value is on this line, right? So we look for the intersection of this curved line and 0.07. 1, 2, 3, 4, 5, 6, 7, which is right there. And
chart only in the first appendices?
the chart, I don't know where it is in your book. I had to pull up, because remember mine looked like a fishnet. Yes. Oh, but is it only in the first appendices? The answer is probably because everything is dimensionless. So it's the same for English and SI. It doesn't matter. So once I find that intersection of the straight line from the reduced pressure and the curved line from the reduced temperature, I carry it over horizontally to the vertical axis. And it looks to me like 1, 2, 3, 4, 5, 6, 7. It looks to me like my Z factor here is about 0.97. Okay? Now, there's always some wiggle room for that, primarily because the charts are really terrible. Now, most of this stuff is computerized so that when you use this in your profession or maybe even in your professional courses, you'll have access to these on a computer. But there used to just be charts, just pages and pages and pages of generalized compressibility charts so that we could narrow in on really small ranges. So, so using this chart is definitely hard on the eyes, and it's also definitely primitive compared to what you'll have to do. Nobody's going to ask you to design a wellhead based on a compressibility that you can barely read. So, so you'll be okay. But the principle is exactly the same. So if my Z factor then is 0.97, that means that this ethane gas at this first set of conditions is about 97% ideal. It means that if I wish to calculate my volume, it's going to be, I'm just rearranging that equation, ZRT over P, which is 0.97, times whatever my R value is. Once again, I have to pick that out of my table, times my temperature, which I calculated to be 559 degrees Rankine, divided by my pressure, which initially is 50 psia. So I need I'm missing my M. PV equals MRT, the way I have it written here. Okay. So hang on just a second. This is 86. Oh, okay, let's just, we'll take a look at this. So what we're only going to be able to find here really is specific volume of my ethane, because I'm not given a mass. So that's fine, just so we know. We need to pick up that value for my gas constant, and we need to have it work with these units. So we have psia and degrees Rankine. So this value, the last column, will work very well. Go down to ethane, 0.3574 in units of psia, cubic feet per pound mass, degree Rankine. Rankine cancels out, psia cancels out. I'm left with cubic feet per pound mass, which is a good unit for little v. If I have the pounds of mass or the amount of the substance, I could calculate an extensive value of volume, but I have to stick with intensive volume or specific volume because I don't have the mass given in that problem. All right. So if I do the multiplication, I take my compressibility factor, 0.97, multiply that by the universal gas constant, or not universal, but the gas constant for ethane, 0.3574. Multiply that by my temperature, 559, and divide that by the pressure of 50 psi. That gives me a specific volume of 3.8758. So I would just call it 3.88 cubic feet per pound of mass. Okay. Now, the other thing, just in closing with this idea, what if it had been ideal? What would we have calculated the V ideal to be? Well, we don't have to go back and reinvent the wheel, but if you take a look at this equation, we have PV equals Z RT. V is equal to Z RT over P. So this value would be 0.97. And so to get rid of the 0.97, if we divide that by 0.97, we would find what our ideal V would be. So our V ideal would be 3.88 divided by 0.97, which would give us a value of 3.99 cubic feet per pound of mass. All right, so in other words, our gas is a little bit more compressed than we would have expected if it were ideal, right? And the difference is essentially, it's a 3% variance from ideal to compressibility because of a 0.97 compressibility or Z factor. Do you guys have any questions at this point?
Yeah, temperature. Are we both in Rankine or Kelvin?
Rankine.
Okay.
Yeah. Yep. Very good question. All right. So this is it for chapter 3. So the last homework set is going to give you a couple of chances to do ideal gas and to do a compressibility factor. So I think you're probably pretty familiar with ideal gas, so I'm going to give you just one, and then I'm going to give you a couple with the compressibility factor. And you can certainly use a compressibility chart that you find online, like the one that I just used, because anytime you print these out, they come out kind of nasty, and obviously the one in the book is kind of illegible, so we don't want to mess with that too much. Okay, this problem is can be quite simple. 388, it's a really good problem for talking about the compressibility factor. I would like you to do 381E, and I'll just alert you, this is the kind of problem that you'll see on an exam, where I compare the one that made my other students so upset with me, the ideal gas equation, the generalized compressibility chart, and the refrigerant tables. And I want to do one in English units as well, or excuse me, SI units. Let's do 384. It's hard to beat that one. All right, and then I'm just going to give you, these both have an ideal gas component in them. You have to do an ideal gas calculation and a generalized compressibility equation. So I'm just going to give you one problem that's purely ideal gas. 372. I'm a little slanted toward SI problems. I should probably change that to, let's see, let's do 74E instead. We have an automobile tire. It'll get at the same idea, only we'll have a little bit more fun with units. Okay? So we have 374E, 381, 384, and 388. And that will be the last homework from chapter 3. So in here, I am not collecting homework in between. That'll be saved up for the exam. And we'll start with chapter 4 on Tuesday. So in the meantime, have a great weekend. Tuesday, no, we're fine in here. There's a region, did any of you guys when you were in middle school do math counts? Yeah, it's a contest for middle school students. And I'm the regional coordinator. So the regional math counts competition will be held here Tuesday afternoon, but it won't affect us. So we'll be here as usual, so as not to disappoint you, especially James. So, all right, I'm going to turn off the streaming, and I'll post this vodcast, and we'll see you guys Tuesday.